purpose of this lab was to explore an object moving at constant velocity without changing direction. An experimental model and a computational model were constructed to describe this movement. For the soccer ball in the experiment to move at constant velocity, it must be assumed that the total pushes and pulls acting on the ball from the surroundings equals 0. This assumption comes about because of our knowledge of Newton's second law. His law that final velocity equals initial velocity plus F net divided by mass times the change in time tells us about an object's motion in the future. Because the total pushes and pulls on the object equals 0, or F net equals 0, the right side of the equation is left with only the initial velocity, giving us that final velocity equals initial velocity when there is a 0 net force acting on the system. The experiment displayed that the ball rolled at a steadily slowing velocity, so it can be concluded that the experiment does a fairly decent job of following Newton's second law. In my experimental model of the object rolling at constant velocity, a few specifications were set in order to track the ball's motion. The calibration stick, here, was set to the soccer ball's diameter, letting tracker know the relative distances in the video. A coordinate axis was also placed to show that the ball is moving in the positive x direction. If I were to flip the orientation of the axes, the ball would still be moving in the same horizontal direction, but toward a different axis. For example, if I were to call the horizontal axis the y-axis, the ball would instead be rolling along the y-axis and perpendicular to the x-axis. When I play the tracker video, the object's path is also tracked and simultaneously graphed in a position versus time plot. This is the computational model created to display the moving object's motion. The initial velocity used in the model was the same initial velocity calculated from the experimental model, the data of which was obtained from tracker. The model shows an object truly moving at a constant velocity in the positive x direction, because the net force was set to 0 and the velocity was initially positive. This is evident by the model, showing the object's actual straight constant motion, and by the position versus time graph, which was a constant slope. The constant slope of the computational model's graph indicates that the object moves at a constant rate throughout the allotted time. The computer model displays the ideal motion of an object with a net force of 0 acting upon it. The experimental model, although very close, does not maintain a constant velocity throughout its motion. This result implies that there must be some outside force or forces in the opposite direction of the motion acting on the soccer ball. I placed all of the data obtained from this lab into a Google spreadsheet. With this information, I was able to plot a computer model results versus the experimental results graph. In the graph, the blue line represents the experimental data, while the orange line represents the models. As it can be seen from the graph, plotted as position in meters versus time in seconds, the experimental data deviates away from the straight line made by the computer model. So the computational model does not completely work to predict the observed object's motion future in the experiment. This can again be understood by Newton's second law. Since the final velocity is lower than the initial velocity, it can be assumed that there must be some net force in the opposite direction of the soccer ball's motion. This opposing force is possibly the force of friction. Friction acts against the object's motion, slowing it down, and accounts for the results observed in the experimental model. So by Newton's second law, we can conclude that an object moving at a given velocity will remain at that velocity, unless some opposing force from the surroundings acts on it. If there is 0 net force acting on the system, an object will move at a constant and steady velocity.